morning session. We'll start with Professor Paul Bressler from Los Andes, and he's going to speak about transgressions in Courant algebroids.
Thank you. Well, thank you very much for the invitation. It's a pleasure and the privilege. So I think I will not outline the plan. I'll just proceed with it. So part one is I'll recall the definition of what a Courant algebroid is supposed to be for reference. Where is it? So I will a word on notations. So there will be probably only one manifold involved in the whole talk, so I'll call it X. So this could be well, if there is another, I'll call it Y. Right? So anything you want. I mean C infinity or real or complex analytic, or even possibly, say, a smooth algebraic variety. I'm thinking over complex numbers normally, I'm sorry. So I'll write, so for corresponding functions, I'll just write this, but I'm thinking always complex valued functions, although for these purposes it's not important. So C infinity or analytic functions or so this is functions. Now, right, I use standard notations. Tx is vector fields, but if you're thinking complex valued functions, I guess they're like complex valued. I mean, so vector fields. Forms look like this. All right, so what is we're going to give a definition. So what's a Courant algebroid? So, well, it's more like what's a Courant algebroid structure on what? So you take this is supposed to be letter Q. What Courant is like it was many years ago, I said Q and that was it. And I later found out it starts with C, but. So you take a module over functions. So for example, I don't know, a vector bundle, if you like, not important. So, so you have certain structures, right? So first of all, on it, I'll use this to differentiate it from something else, a bilinear operation, which is only bilinear over numbers. And it has the property of being a Leibniz bracket. So it satisfies a correctly written Jacobi identity, but is not skew symmetric. So I guess, I'm not sure, probably the one that I'm thinking of is left Leibniz, let's say, but it's not that important. And so this thing, I mean, it's supposed to be an algebroid, so it acts on functions via, I guess what one calls probably the anchor map. So this is linear over functions. Well, I mean, this is a Lie algebra, so in particular, Leibniz algebra, right? So linear map of algebras, I mean, in the sense of this. Then it gets more strange. So then you have a pairing, which is bilinear over functions. It's a symmetric. Okay, and then there is another piece of that, that there is a map, which will suggestively be called, this is like adjoint to transpose, so it suggestively calls this. Okay, and that's it. Thank God. Right, so, all right, so all of these combine into there's no conditions. I mean, not. I mean, one could. So subject to. Well, so first of all, you combine these two, and the answer is 0. Well, then there is kind of a Leibniz rule for the bracket, a little bit one-sided, because, I mean, you have this operation, you can multiply by functions, so something like okay. So you produce a vector field out of the first one, hit the function with it, and multiply the. Okay, then the relationship of the pairing with the bracket, so it's like invariance of the pairing, which looks like, well, the usual. Yeah. It's just the kind of a Leibniz rule, I guess.
This is the curly bracket.
I knew it. It was a bad idea. Right. Well, then there are. Can I continue here? Well, then, of course, the question arises how all this interacts with, the forms. Sometimes this is expressed like this. This, you have, of course, the derivative, but you can, so to have this map is the same as to have a derivation here. You can rewrite some of this in these terms, which we are coming to that. So, for instance, how do we act on a form? Well, I mean, we know how to act on the form. Namely, you take the lead derivative, you take Q, produce a vector field, then you hit the form with it, and you put it back in. Or, for instance, how do we pair with the form? Well, we know what to do. I mean, calculus is calculus. So that's supposed to be a function. Well, I can certainly produce a function out of a form. And finally, the funniest of all is this. So this bracket is not skew symmetric, but not completely. So if you symmetrize it, you don't get 0, but you get, well, more or less a form. I mean, this expression under the anchor map goes to 0. So, I mean, it makes some sense, right? Okay. So, I just did this for the record. It took a little more space. This, I think, normal people, they can perceive this as quite weird. And I think I can relate to that. I mean, because where does this come from, right? I mean, how can one think this up? Well, there's no need to think this up. Okay, this exists in nature, but not in nature. So this is, I will not explain this in detail. So I'll do something else. But roughly speaking, this was known to Professor Dirac. He said one-dimensional, one is this one. Field theory, there is a notion of Poisson algebra, which can be formalized into, there are what is it called? Vertex Poisson algebras, Poisson algebras, there's many terms, and this is what happens in low weights, literally. Just change of notation. All right. Now, there was this question about these conditions, non-degeneracy. It's not important. For example, imagine the whole thing is equal to this. It's okay. It's possible. I mean, there are the interesting possibilities. Anyway, so what do I mean by even transgression? Because we're going to talk about odd. I mean, I don't think this is in quotes. So what is this supposed to, what does it want to be? It wants to be something that is too complicated, like 15 different operations. Right? It wants to be one thing. So so I've described something very, very non-scientific. You can ask me about technicalities later, but this is what I think it's quote-unquote well-known in a sense, right? So it is certainly not scientific, starting from the very beginning. All right, so just as an example, so you take your manifold, take loops in it. It's another manifold. And so you have these maps, evaluation to x, so it's just loop and some number, you plug it in, and there is projection. So this will be denoted for projection. Of course. So generally, I mean, you have station, well, for all kinds of mapping spaces. So by this one usually means, I think, is a process which I'll symbolically denote like this. Well, the idea you lift something from here and you integrate it, so to speak, along, and you can apply this to various, I don't know, differential forms or whatever. So we'll look at some examples. So the non-scientific part begins right here. So what is this? Nobody knows. What is important is to agree that this has functions, and you can do calculus on this just like always. So if you agree to that, we're good. Right? So for instance, so for instance, I can do the following in general. So I can take some, I know, E, like a vector bundle or something, on X, and I can go per F E. And you get something that lives, I mean, it's a little big. Well, the space is big and the bundle is big, right? Right? So this has, well, here's a famous computation. For instance, if you do this to vector fields on X, there's a canonical isomorphism between this and vector fields on the loop space. Yeah, let me explain. A well-known fact. Well, I mean, so this is some kind of a bundle. So let's look at least at the fiber. All right, so who is this? I know, you take a, well, it's a well-known. I mean, you take the circle, right, and you pull using this loop vector fields on X to the circle, and you take global sections. I can draw a picture. This is the manifold, and here is the curve, and at each point so you can move the curve. So, right? So on the other hand, this is, well, quote unquote, fiber of this, obviously. No. These are parameterized curves, first of all. Just a space of maps, as is. Right. So, but it's even better. So, of course, this procedure, it's not clear how this interacts with differential calculus, but it does, trust me. Right? And so this automatically will, so the bracket on v bracket on X will induce an operation here. Well, this is vector field, so there is a leaf bracket, and these are identical. So, I know, with brackets. Okay. It's a well-known fact. Okay, well, for instance, so it's another, I was planning to later, I guess I will have to erase some of this, but you have to keep in mind, this is an important ingredient always. Then, oh yes, and then the integration, for instance. So suppose I take, I don't know, k forms on X. Then I can put them here. Well, there is this map, right? We integrate out the circle variable, so you get a k-1 form on the loop space. Also quite famous in the study, say, of the Ram complex of the loop space. So we'll, of course, need only k equal to 1, in which case here you have functions. Where is only k equal to 1? Okay, so this is all we need. Oh. Well, something has to go. Unfortunately, I guess the definition. But this is very sad. I didn't realize it takes half the space, but it's testament to the fact that it's much too long. Okay, so what do you do? So now, Courant algebroids. So you have this, well, you have this Q, and there is this P. Well, P is not, part of Q, but there is such a map, just for illustration. And here is the other map that is important. Okay, so we take this and we apply the process. So here we have some familiar things. Well, here I don't know something. And here, well, in the first example, we already see vector fields, so that's good. Okay, on this we have the integral, which gives us functions on the space, oops. And we take the push out. So it's basically this plus this modulo the image of this kind of diagonal, which I'll call tau q for transgression. Okay? Now, because this map, remember, is 0, so in fact, this also has a map to vector fields. Well, again, this is not scientific, but this operation that we had on Q, well, the bracket, like with the vector fields, it induces an operation here, which is still no good. Then it's easy to check that, in fact, it descends to here. And the new operation, so here we had this, I'll just put brackets, is skew symmetric. Now it says, just checking quick quiz question. Why is this skew symmetric? Have you been paying attention? It's still on the board. Yeah, because the whatever was non-skew symmetry is an exact form. You can integrate it all you want, but only 0 comes out. Right? Okay, so but here you see all these features. So first of all, this is, this is a Lie algebroid with this anchor. But there is an extra feature which is typical for these. So here, here there is, of course, 1. But it's not maybe as such so important. It goes to an element here, C, a section, to the central section. So it's always, there is always 1. Could be 0. There's always a canonical, a central section. So that's kind of the framework, the Lie algebroid with a central section. This should remind you of the following, maybe. So if, well, it will be true, say, if Q is exact. Let's say, so exact means that, that this is, the composition is 0, but even better, it's actually those two maps form an exact sequence. Well, then this business looks like this, right? There is, the functions, then there is this tau q, and then there is a vector fields, and it's also an exact sequence, and should remind you of, roughly speaking, is a T algebra. How do you spell this? Like this? Algebra of a line bundle. It's about roughly the right size. Sometimes it is. It's an example of where you have a central section. They're all like this. But more generally, if you divide this by this, you don't see T, you see some other algebroid. It happens. So this is the source of all of your Kac-Moody algebras combined, for instance. Yeah. So, yeah.
This possibility question, is it some kind of enlightened version of my old calculation with trouble?
We talked about this. It is, no, this is also, dates back to the same time. Well, this is a yes, it is, but this is not a scientific calculation, right? But you can make it scientific at the expense of, killing off most of the audience. But in the language, I tried to convey this to you. I remember it must be like 15 years. No, so if you make this scientific, it's a statement about some two adjoint functors between something and something. It is one of them. But the interested parties, we can discuss this later. This is all horrible, because to make this scientific, you have to, it is like some background, which goes under, I don't know, formal calculus of variations or something. Or, there are different names for this. But the biggest problem, the very beginning, is how is this a manifold and what do you do with this? If we can agree on functions on this, after that, it is all true. Okay. But now, my first comment was about this, right? That if you make this scientific, it works the other way. So there are these things invented basically by Professor Dirac. And so if you look at the little piece in there, then you see a definition of a Courant algebroid. So there's no need to, invent anything. Professor Dirac was pretty much right. But but this is like this idea framework, right? So you have a Lie algebroid plus what I would call a marking. I don't know what the terminology is. What do you call it? Lie algebroid plus a central section. I call it a marked Lie algebroid. Doesn't matter. Okay, so instead of all this infinite dimensional nonsense, I mean, we can begin to do odd version, which is finite dimensional, but a little bit differential graded. So I worked on this. I have, well, my former student, so I should mention Camilo Henrique, and we keep working this general direction. Right. So by the time he finished writing his thesis, it was too late to rewrite it, but I realized that this whatever is written there can be in general packaged in roughly literally the same way, but with a few twists. So okay, so odd transgression. This is 100% scientific. I mean, in the sense it doesn't suffer from these, little problems, and maybe is more usual. Okay, so this is unfortunately differential graded. So one uses the words like differential graded manifold. So what does I mean by this? So I'll write stuff like this, not really ever. Right? So there's a space, an actual manifold, and some functions. And this is a commutative differential graded algebra, which I will assume, let's say, right off the bat, is bounded below in the sense of grading. Not, there will be one key example where this gets into negative degrees. So, but let's say, I mean, it's restrictive. Maybe it's a good thing. I mean, okay. So locally, should look like this. So it's just normal functions times symmetric algebra on some. So where E is finite dimensional, meaning the whole thing, graded vector space. Yeah. Okay, well, so I move on to examples. So example number, I know -0, that's -1 is, so of course any manifold in the usual, normal manifold, I guess, is like this. Sure, my favorite, maybe one, okay. My favorite manifold, one little vector. One little vector is like this. So the space is one point, I don't know. Yeah, and the functions look like this. It's numbers, you attach a variable, and you differentiate with respect to it, and the variable is degree -1 and square 0, just in case. This plays a key role in the whole business. Oh, and there is a It's not partial. You differentiate. It's functions of epsilons. You differentiate. I mean, structurally, it looks like this. In degree -1, there is epsilon, and there's multiples of that, and then there is, so epsilon goes to 1, which subsequently goes to 0. Or it's nothing else, just 0 and -1. So it's basically the identity map.
Yeah, but just
Yeah, so derivative of epsilon is 1, derivative of 1 is 0.
Yeah, but why do you write the epsilon? So is it like part of your function?
No, this is a differential graded algebra. I mean, I have to have a differential. For me, it's non-zero.
No, but it's not all x.
Yes, this is. Oh, this is. This is it. Yeah, right. That's what. No. Sorry. There's no. This is not same as this, not unrelated. We're going to combine the two now. Well, then there is this famous, well, this popular example. Well, I call it X sharp. Some other people call it, I think, something like this. But I don't know. I don't have the heart. You know. I read this, and I think Bailenson calls it X sharp, so we can call it X sharp. Okay, so it's X, and here you have the Dirac complex of X for functions. Okay. Okay, so and then let me state a well-known fact. Well, well-known is in the literature, so folklore. It's not hard to prove anyway. So, right. So, mapping spaces. So, in general, of course, mapping spaces are not representable. So, so this is like under well-known. I know. You know, like everything. So, mapping space by definition is this. So you have two things. Who? Oh no. So C and B, and I would like something which is like mapping space. So what is this? It represents as a function of A, right? Well, this is by adjunction. If you have products, which you do in this case, for instance. So if you know what A times B is, then is what this is supposed to be. Generally speaking, is not representable. However, well-known theorem, you know, that, so I take X, the usual manifold, and I map this business to it, and this is represented by X sharp. It's called the universal property of forms. Not hard to prove, but what is hard is to find the correctly written down proof in the literature, as with many things. Okay. All right. So we're basically done. So the question arises, if you believe this, the question might arise. This is all like classical differential calculus. So the question might arise, what is the evaluation map, right? So supposedly I have the evaluation map from this times this into X. Now, all these spaces, mind you, as the space itself is X, always. This is X, this is just one point, this is X. So the issue is about what this map does, right? It takes functions on X and maps them to functions on this product, which I guess is not hard to see, is you basically take your Dirac complex and they join this variable, but the differential now has two pieces, right? I mean, it's d epsilon. Right? This is supposed to be a map of differential graded algebras. Map is like, you remember that this has degree -1. This is kind of important, right? Because take F, and basically you write down the first jet of F. Namely, it's F plus, well, here, this is a delicate matter, I think in this order. Here, order is important because you just flip these two, and then you have signs propagating to the rest of your life. No, I think, because I'm not very bad with this, I think this is good because later on, but I'm not, there's no, I checked in the text. Seems okay. Okay, so I think we're okay now. This is simply, so this part, this is just like J1. If you like, in this notation. well, we're not going to do, vector calculus now. But, okay. So this has all the right, features. What I mean is analogous to those that I just erased. For instance, well, in general, what can you do? So first of all, and then there is the projection. Well, the projection, of course, is not a huge surprise. So on functions, this is an algebra with the Dirac complex. It's like, right? So what is this process? So what is this, first of all? Well, it's like this. You take E, and you extend scalars to this. So remember, every time I write this, just the Dirac complex. But the only thing to remember, this map is slightly more non-trivial than you might think. But it is, well, the enthusiast can check that it's a map of differential graded algebras, which means something, right? There's no differential on this end, so the stuff cancels out, which maybe if you think about it, like this df cancels with this df, or something like this, right? So, so this is this part only, right? But then this doesn't mean anything. It just means this is like, restricted to this sitting here in a trivial manner, kind of, right? So it's viewed as a module of the Dirac complex. Okay, well, so after some thought, so this is in general. For instance, I claim we're not going to, if you know what you're doing, this is an easy, I don't know if I can say enjoyable, but exercise. So for example, you take this, you get this. So, well, you have to know what the derivations of the Dirac complex look like. They look exactly like this, together with the brackets, in the sense that here we'll talk about more. It's easy to introduce. It is a systematic way to introduce, these differential operations, which become bilinear. Well, this is just that they're all order 1 operations, and this straightens out that completely. Right? Not everything, but anything which satisfies some kind of Leibniz rule becomes linear after that. By direct compute, surprises me as well every time. But so this is the algebras. This has a Lie bracket. This acts by derivations by definition. Okay. Well, but of course, this process goes much further. Yeah, all of everything, all derivations of the, but you see the size, all right? There's two copies of Dirac complex times this in there, right? One shifted by one respect to the other. Well, it's exactly what comes out of this, right? In size, at least. All right. Right. Well, you can go on and on. For instance, no, you ignore. Well, you don't ignore it, right? The answer. But that's a quotient, right? No. What do you mean quotient? No, this viewed as a module over this.
Yeah, but for that you're using the embedding of OH sharp in the product.
It's just times 1. It's one of these, yeah. This is like.
Doesn't that
No, the underlying vector space is the same.
My question is, if you're using the projection of x sharp into the product of x sharp.
There is no projection. Yeah, but the pullback of functions is simply the inclusion of this in here as multiples of 1. Right? So, I mean, the space itself is the same space. In principle, it's a modulo over this bigger algebra, right? You don't care, it's just...
It's not standard, right? So if you take OX and you apply this procedure, you get...
You see OX times 1? No. What do you mean, not no, this one is funny. Maybe. Well, maybe it's not funny. But that one is a triviality. Yes, so for instance, so more generally, so for instance, you start with the Lie algebroid on X. You do this to it. So there is a basically unique manner in which you can define, this bracket induces something here, which that is an example of. Well, it's a Lie algebroid. So plus, induced, let's say. So let me call this, I'll call this A sharp. I'm sorry, some of these notations, I don't know. If you have other suggestions, I'll be happy to. Okay. So algebroids go to Lie algebroids. So this is in general. Also modules. So for example, also you can, I don't want to formulate this. So if you start with an A module, then this is an A sharp module. And so on and so forth.
So if you apply this to a Lie algebra, over a point, then you get the way.
Let us wait for a second. Yeah. Okay. Well, right. Of course, one point space is also a space. I totally agree. So X equal to 1 point. Well, then the result is, so this is just the complex itself looks like this. It's like times epsilon. Right? So as a Lie, if this is a Lie algebra, then it's the famous Lie algebra with your old Lie algebra with epsilon attached. Okay, well, it's not so, but the most, again, the more interesting feature of this, this is not terribly deep. You have to write down the correct formulas. You understand what you're doing is not so, for the calculus. The more interesting thing is this. So we need this, right? So suppose I take forms, let's say, on X. So I do this. Okay, so then, I'll draw a picture. There is a map. I'm sorry, I called it integral. I realized somewhat later that maybe it wasn't such a good idea. Maybe some other symbol would have been more appropriate. So I don't know. So this means shift down, right? We'll be interested only in k equal to 1, in which case this is 2. So this business, the Dirac complex, starts in degree 0. Right? And this starts in degree negative k plus 1. We'll do an example right now. Okay? So what is this map? So in degree -1, there's nothing below degree -1. So here you have a copy of forms, if you like, times epsilon. Yeah? Okay. And here, which is why it's k plus 1, you also have in degree -1 k forms. Right? Because the kth component minus first component of this is k forms. Right? And this map, well, is exactly one. I mean, I don't even want to ask the control question. I think there's exactly one map that one can, imagine, called the identity map. Right? And then you want this to be a map of modules, where it's not a lot of choice. So, for instance, next to it, what happens? So here you have k forms now without epsilon, and you also get a copy of. So this is, and this, I mean, everyone usually focuses on degree 0. I understand. But this is k plus 1 forms here, right? And this is the part of the differential. Right there, so this is D. Well, I guess this is D. Well, we could later on in private discuss the relationship of D with the integral, but not right now. But we're going to use this with k equal 1 presently, okay? So this extends in a unique manner to a map of modules. That's it. So now I can perform the same stunt as before. So suppose I take this Courant. Mine. What time is it? 4. Yeah. I mean, I have this ambitious plan, but to demonstrate how you can replace Courant considerations by these, but I think it might be a little short in time.
This integral,
It's just exterior derivative. It's just D.
so this kind of integral have nothing to do with Bursztyn integral, picking top element.
I think maybe in some very degenerate case, like low dimensional. No. No, it's not that. It is not, no. I mean, one needs to look at what goes on in the even case. See, what I described to you in the even case used like circle, right, actual integral. This does not exist. This whole theory is local on the circle. In other words, it deals with curves, arbitrary curves. Oh, you say, well, where's the integral then, right? What is local integral? Local integral is D.
But then this is not like a Bursztyn integral of the
No, there is no, I mean, no. No, there's no, I'm sorry, I realized later that was a big mistake, this piece of notation. I can call it odd residue, I don't know. Which is what that integral was in the first place. That integral before was residue, it wasn't integral. And this is also kind of, okay. Anyway, so always like before, so you have your Courant. I draw these things just for, comparisons. Right? 1 forms. Okay, so we hit this business like before with this procedure. So there is Q. Okay, well here, if you believe me, I mean, you see the vector fields. Here we see I mean, the reason I mentioned this, originally there was this idea of higher dimensional variance of this, where instead of 1 forms, you'd be putting higher degree forms, but this is certainly not the way. Well, we apply integral, and we wind up in the round complex shifted by 2, I guess. And the output of this, so this is defined as a just push out. You call this tau q. And again, because, I should mention, so what's automatic is this, that, well, this map is 0, I mean, right? Yeah, so you still get a map to here, to the vector fields. And blah, blah. Well, the operation here, of course, gives an operation here, which descends to here. And this is actually, I mean, to write this down is easy. Let's not do this. I mean, there's some bunch of rules on, like, simple things, and then big Leibniz rules. So if you bracket two general expressions, this occupies maybe, half of this space. Of course, checking, like, Jacobi identity, if you are into this kind of thing. This also occupies space. You said the Leibniz rule this, Jacobi this, for like half an hour. Signs are important. So if you're not good with signs, I wouldn't even bother trying. Because, there's supposed to be some big sum is 0. And it comes out like twice what you started with. Why? All signs are wrong. Right? Well, anyway, I mean, so again, the resulting operation here is skew symmetric. I mean, it's a Lie bracket. Why? Same reason. This is D. And remember, non-skew symmetry was exact. So DD is 0. So this is, first of all, it's a Lie algebroid. But again, this is this feature that maybe one takes like 1 here, which is in degree -2, by the way. And this goes to like some global section C, let's call it, plus, C, which is, in global sections in degree -2. Okay, well, we'll look into this whole arrangement in a second. Right? So let me call this, marked Lie algebroid. Right? So this is the marking. It is important. I mean, the same thing with 3 times this is not the same as this. Right? I mean, okay. Yeah, so with the operations, okay, I can roughly tell. First of all, after maybe 15-second inspection, yeah, so this, of course, is kind of derivative, I mean, in the sense that, there was always always, since a long time ago, this, for some reason, issue, why that a Leibniz bracket wants to be a derived bracket, right? Because derived brackets are that way. What is the right bracket? I mean, this realizes the dream, first of all. Because if you look at this business in degree -1, so in degree -2, see, this is a normal thing. So this modulo this starts in degree -1. So the only thing in degree -2 is this C. No. Anything like this starts in degree -1 automatically. This whole line starts in degree -1, goes up. Because epsilon is the lowest, right? But this is shifted by 2, so the 1 is 1 below. It's the only thing that's in degree -2 is this, the new feature. I would even suggest, for our purposes, this whole thing with, so Lie algebroid, yeah, just words. Lie algebroid should mean greater than or equal to -1. Let's agree. And marked Lie algebroid is great. Well, it looks like this. You take it, modulo the marking, and this is a Lie algebroid. Right? And the marking has degree minus, the C is degree -2. Yeah, it was normal as usual, right? There's nothing funny. Like before. I mean, okay? Yeah, so this business is Q, first of all. Right? So this is degree -1. And there is degree -2. Well, maybe it's a good idea to think that this map is injective, I mean, if you like. Right? In degree -2, there is only a copy of functions on X. And then there is a differential, which is our original this del that I mentioned. Then there is more, right? Okay. So this maps to degree -1 of this, right? Which is vector fields, and receives a map from degree -1 of this, which is degree 1 in the de Rham complex, otherwise known as forms. Right? Okay, so so the symmetric pairing, first of all, is bracket -1, so to speak, -1. Well, -1 is -2, plus it's Q-symmetric in this sense. So it's symmetric for normal people, right? And this here is derived bracket well, I mean, just direct check, let's say. It was designed to be this, right? And there's some stuff going on. I know. No, that's it. So now both of these are part of just one big operation called bracket and Lie algebroid. This is exactly the same as happens in the even transgression. All these little pieces, they're modes of one big Poisson bracket. You know, I mean, to take it apart doesn't really make that much sense. It's not even a natural process. Just a Poisson bracket on some functions on fields of some sort. This is just one. This, for me personally, I must share, this is a huge relief. Because I don't need to think, but there's this, there is that. It's just one bracket, satisfies the usual, I mean, it's a Lie algebroid. All right, yeah, so maybe let me quickly mention, I mean, what this has obviously a special, it has a universal property, namely. So suppose I look at these AC, which are these marked Lie algebroids on this X sharp, let's say, right? So with these conditions, right? And here I have Courant algebroids, right? On X. All right, so I produced for you a functor tau, which lands in here, right? Now, what I just was trying to explain over there applies to any one of these and produces a functor, I know, Q. You take the degree -1 part and you write some formulas down, you get one of these. Okay? These are adjoint. And on certain subcategories, they are equivalent, mutually inverse equivalences. These are adjoint. Well, if you don't impose some conditions here, then this simply is not going to be a Courant. It won't make a lot of sense. Well, I mean, so I came to this as a parting thought. Well, in dimension 1. Right? Lie algebroid is something like this. Right? And there's this and that, and there is nothing else. And this should be thought of as like, this plus, it's what it is, a central element added, which is customary in this kind of business. So, for instance, I can apply this very quickly to the favorite notion of Dirac structure. What's a Dirac structure? It's simply a map from a normal Lie algebroid to one of these. It doesn't have to be maximal in some sense. What, you always have maximal symmetry? No. Right? I mean, it's a matter of taste. I think it's best to